first interview in a series from the IEEE Control Systems Society History Committee. We're planning a series of interviews on some of the more famous contributors in the controls field. And today's the first one. We have the pleasure of interviewing Karl Aström. And the main interviewer will be Gene Franklin. He will start off the interview, and then we're going to open up the questions to a panel for the second half of the interview. Okay.
Franklin from Stanford University, and I'm going to begin the interview with Professor Karl Aström of Lund, and as part of this Control History Committee, and to present some of the background and contributions of Professor Aström. Karl, I'd like to start with the beginning, as Lewis Carroll said, to begin at the beginning and be able to come to the end and then stop. and so in the beginning, you were from Sweden. Could you tell us where you were born and sort of how that your early education began?
Okay. No, I was born in a small city in Sweden called Östersund, which actually is in the geographical middle. It's something like 500 kilometers north of Stockholm. And I went to school there, and I went through what we call the gymnasium, which is roughly your high school. And of course in high school I was interested in mathematics and physics. I was interested in languages and many things, but I wanted to become an engineer.
From the beginning?
Oh, well, yeah, I think almost from the beginning. I mean, when I was 10, 15 years old, that's when.
Sure. Well, tell us something about your family now. You have no siblings, I understand.
No, I'm an only child. And my father is a painter. My mother was a housewife.
Mm-hmm.
So we really had in my family no academic background at all.
I see. Yeah. But when you went into school, you say so your favorite topics then were mostly science and engineering, or
no? I was also. I think I was interested in many things. You know, it was very easy for me to learn.
Mm-hmm.
So I discovered pretty that I could do quite well.
Lots of things in school, sure. And tell us, did you have any particular mentor or teacher who had a significant impact on your early education?
Yeah, we had what I remember very well was from the high school time. I had a teacher in mathematics. Mm-hmm. His name was Wigfors, and he was, I think, he was related to the finance minister of Sweden. And he was a superb mathematics teacher. I mean, he was always, trying to push you. Mm-hmm. He was always trying, to do a little bit better and things like this. So he was one that certainly had a big influence on me. I also had another guy. I was in the same house where I was living. There was a guy who had a radio repair shop.
Oh.
And he was
technology comes in.
Technology comes in, and I started to work for him quite at an early stage. I mean, just doing little things in his workshop. Then during my gymnasium time, I was, repairing radios. And he was also a very wild character. So he was taking care of all the electronics equipment. The little town probably had something like 15, 20,000. So he was doing the electronics of the hospital. Oh. And I remember one incident. He had inherited an X-ray tube. And he was also very much interested in photography. So he had the brilliant idea to do an X-ray flashlight. And when he tried it out the first time, he put it under his workbench to make sure that nothing bad would happen. When he switched it on, he lost the hairs on his legs. So he also gave me, he was taking, these sort of courses in physics, the courses where you do it by mail.
Oh, correspondence
courses. I mean, he gave me his correspondence course in physics and in electronics and things like this.
So, and this would have been, what, in early 1950s?
No,
before that, I guess.
Let's see. I think it started in the late 40s.
The late 40s.
And then I went to university in 1953, so I mean late 40s and beginning 50s.
Yeah. Now, in your school, how about what we might say the extracurricular things? Were you a sports fan, music fan, a chess player? Tell us something about that.
I did a couple of things. I mean, first of all, when I was around 8, I think I started playing the violin. Oh. Yeah, so I was playing the violin actually all the time until I started university. But in my first year in engineering school, I gave up. Because I discovered that you can't spend enough time studying engineering, and
And doing violin.
You played much worse than you did last year, and when you're around 20, that's no good. Yeah. Also another thing I did, at that time we did a lot of skiing. So the city where we got snow in the beginning of typically October, and it stayed until mid-April. So we typically we skied after school every day, all sorts of skiing, cross country, downhill, ski jump.
Yeah. Okay. So then you went to the university in 1953.
Yep.
And now was this this is the Royal Institute of Technology?
Yeah.
I understand. Is this a technical institute, Karl?
No, in Sweden it's been in the same way as in France, that we have had separate schools of engineering. We have had the regular universities, and then we have had the engineering schools. And at that time there were two engineering schools. One was Chalmers, and the other one was the Royal Institute of Technology. And then the typical program was that you started, and then you went to a 4-year program that was, I would say, it's roughly equivalent to master's degree. So you do a thesis, and there's no way to do bachelor and things like this in between. So it's an integrated program. You come up roughly with a master's degree.
So you're sort of committed to a master's degree.
Yeah, you're committed
after gymnasium.
Exactly. Yeah.
And what was your major there?
I did. We had something which is very unusual. It's called in Swedish teknisk fysik. And you hear from the word, it's roughly engineering physics. Mm-hmm. And one reason for getting in there is that it was the toughest place to enter.
So a challenge.
Yeah, it's a challenge. They only, at that my time, they only took in 20 people from all over Sweden. And my class quickly reduced to about 13. And it's typical engineering with a very heavy science background. So, we were taking a lot of electrons, but we were also taking, strength of materials and a lot of the sort of mechanical engineering types.
So then when with a class that small, everyone was taking the same curriculum. Is that so?
Yeah. Oh yeah.
So it's a fixed.
Well, there was, you can say it was roughly 4 years, and for the first 2 years, everybody in that group took the same curriculum, and then after 4 years, you could specialize. You could, focus. If you wanted, you can essentially get rid of everything that had to do with mechanical engineering, or you could make a very heavy focusing on mechanical engineering, materials and stuff like this. So quite a bit of flexibility.
A bit of focus there. What about the laboratory or experimental experience? Were there lots of tough labs there?
Too many.
Too many.
Yeah.
Lots of nights. Huh?
No, I think for example, I think we did something like 150, close to 150 physical experiments. Long time of writing, and also a lot of time to write the reports. And they also had a very mistrusting system. So you always had to take copies of your primary data. You have to sign it. And then you left one copy of the primary data at the university, and then you took another copy with you home. That was serious business.
So it was hard to cook the books.
Exactly.
Turning in their...
well, even so, the books were cooked.
And at this time now, how about the recreational side? Skiing continues.
Well, I continued to do skiing. So I went home to my parents, on vacation. So I continued to ski, and also we did a little bit of rowing because the university was quite popular sport at the time. Mm-hmm. Otherwise, it wasn't so much.
And how about the social life? I've seen you dancing in tavernas in Greece. You've learned this?
No. I mean, it was a nice social. There were typical things. I mean, there were dances on the weekends, and there were quite a lot of parties. Uh-huh. So I think one thing I really enjoyed from my student time is that you really met your professors with a class of only 13.
Sure.
And also it was tradition. Say for example, once a month or something like that, was a dinner with the students that were. The higher classes and then the lower class. So it was typically something like 50 people would show up. And quite a few professors showed up. I see. And I would say you learned quite as much, by talking to the professors when you met them socially about what's important, what's fun, what you should do. So it was very good from that point of view.
And as you say, in a small group like you get to know your professors very well. Were there particular mentors that you would identify?
Oh yeah, sure. I mean, there were actually. I would say that actually most of them were characters, and of course I had some very good professors in mathematics, and we had very good professors electronics. There was one guy, Hannes Alvén. It's one of the I think one of the very few Nobel laureates for Sweden. I mean, he invented magnetohydrodynamics. So he was the one that was very interesting. We had another one in mathematical physics that was very good. We had one in probability that was very good.
Was it Grenoble?
No,
No.
I'll come to that later. No, his name was Essén. Carl Gustav Essén. He was. I don't think he's very well known here, but I'll tell you a story about him. He was extremely shy. So when he was lecturing, he had a little black book, and then he was sort of sneaking up to the blackboard, and then he was looking at this book like this, and then he was writing, speaking very good, but very well organized. So he was, for example, we told him we would like to know something about stochastic approach. Oh, come back this autumn, I'll fix it in this course. So then he had learned about it. But when Kolmogorov visited Sweden, so he came off the plane, and then the first thing he said, "Where is Carl Gustav Essén?" And he wasn't there. He was specializing in the central limit theorem. And you know, there's a coefficient in the central limit theorem. In his dissertation, this was up to a few hundred, and he knew it was going to be 1. So then, gradually over the years, he was bringing down the coefficient in the central limit theorem until it became 1.
Yeah. Very. Now then, from you graduated. Now you said you did a thesis.
Yeah, I did a thesis.
What was your topic?
The mechanics of drops and bubbles.
And this was defining the shapes of bubbles.
It actually came from. I was at that time working in the mechanics department. I was doing a lot of teaching when I was there. So this was done in the mechanics department. There was a professor there named Bengt Andersson. He was doing hydrodynamics. And the problem was this, if you see it nowadays in hotel rooms, if you have a tube like this, transparent filled with water, and then you inject air into it, you get bubbles raising up. And these bubbles look like umbrellas. They are almost a spherical part, and then they are cut off there. So what I had to do is that he said, okay, well, can you try to figure out, the shape of the bubbles when they are
predict that shape.
Predict that shape. So I was doing, classical mathematical physics.
And from the Institute of Technology, then you went next to the Navy. Is that so?
Well, after I graduated, I did my actually I did. I was enrolled in the Navy before I started the engineering school. So I did in the summer between high school and the engineering school. I did learning to run and to do all this sort of military routine stuff.
I see.
But then when I was finished, I was. I had to do my military service in the Navy.
So there was a compulsory military service, was it?
Yeah.
After you finished
Well, actually, it was a compulsory military service, and I think you really had two choices. I mean, either you can do, so to say, typically fairly boring army job, or that would take something like 9 months or 6 or 12 months, or else you could apply for some special service, and then that took longer time. So you had a trade-off.
And you took the longer service, and what was your assignment there?
I was assigned as an electrical engineer to the Navy. And that was at the time when Swedish Navy had great plans. We were going to build lots and lots of destroyers. So they trained people to take care of everything on a destroyer, from the telephones, the sonars, the radars, and that kind of stuff. So we had essentially 1 year education right in the center of Stockholm, where we really had to learn this kind of thing. For the Navy,
the electronics,
and also things like sonar and stuff.
Yeah, sure.
So that was good training.
And then were you taking courses at that same time? You said you were taking courses in electronics, so these were taught by Navy personnel.
Well, they were taught by Navy, and also in Navy. We were only, I think we were about a dozen of us. And some of the people coming in, we didn't think they were very good teachers. We made a deal with the guy in charge of this. So we said, okay, how about letting us do the teaching? And you save money, we get better courses.
So you taught each other?
We taught each other quite a lot. And to me it was a shock, we were trained, for example, to be able to fix up radars. And the crew we had were people with very little formal training. And of course, to me, coming from the university background, it's quite surprising that you can have very little knowledge about, but you can train people you must know about this.
Sure. I was an electronic technician myself in the Navy.
So the idea that, by learning that this was the two done, when the grid goes up, the anode goes down, and Ohm's law, and learning to read a schematic diagram, you can actually fix radar. That was a big shock.
And then you went to Stockholm University?
No, I went back to the Royal Institute again after my military service. But also at the time, when we studied, you always have extra time. So when I was in engineering school, we took courses in mathematics and probability theory from Stockholm University.
Okay.
So in there, for example, we had one of the Swedish geniuses in mathematics, Lars Hermander. He gave courses in functional analysis, measure theory, and things like this. And then Ulf Grenander, he gave courses in stochastic processes, probability theory. So those of us who were theoretically oriented, we went there, and took quite a few of the courses. And that continued also after my military degree. So and also during my Navy time, I still had contact with the school. So I remember I taught the first Swedish course in sample data system in 1958.
Oh.
Yeah, and I did this during my military. So I got a couple of hours off from the military to go to the school to teach sample data systems.
That's great. And where did your interest in control begin?
Now that's a strange story. I was in mechanics, and I think it was probably around 1955. So I think I was in my third year in school, university.
At the Royal Institute of Technology.
So I started in 53, and I think this was around 1955.
Okay.
Then my professor, he was a lot involved with the defense organizations, the one in mechanics. And then
this is the bubble man?
Yeah, the bubble man. And he came to me and said, well, there is an interest in inertial guidance and missile guidance of the defense. And they would like to put together a team of people. We don't know what it is, but they would like to put together a team of people who can do something with that. And since you're good with gyroscopes, I think gyroscopes are the thing, so why don't you come to your class? So then they formed a team with a few professors from the Royal Institute of Technology, several of the senior engineers from the Research Institute of National Defense, and they founded something that was called the Theoretical Inertial Guidance Group. And the idea was that they wanted, number one, to look at the guidance systems for the missiles that were planned to be built. The idea was, at that time, Sweden were essentially developing nuclear weapons.
Sure.
And the idea was to have missiles, and they wanted to have people to do guidance with this. And they also had, Air Force people, and Swedish industry was involved a lot with that. So they started up this group, and of course we started to read about. There was one course in control at the university, but not very much. But we started to read about this. We started to learn about it. And also, they brought over people from the United States.
From the instrumentation lab?
Yeah. Draper himself was over for about a month. Several of Draper's people were over.
I see.
So when I was there, I was put in charge of being, so to say, the local handyman for Draper.
Oh, I see.
To make sure that you pick him up, make sure he gets to the right places and things like this. So that's really how I got interested in control. So when we started to look at this, and it was very fast. I had a very good friend, his name is Svante Jonberg. We were classmates from the engineering school. He was also involved in that. And between the two of us, we read a fantastic amount. And so that started around 55. And when I was finished with my military, I went back to the university to get my Ph.D. And that was at the time I was working very intensely on this inertial guidance type of problem.
And what was your PhD thesis topic?
Oh, it was... it's called stabilizations of platforms with single-axis gyroscopes.
So it was intimately connected with the inertial guidance problem.
Yeah. And we did a couple of neat things. You asked about my control. In connection with this, we had a collaboration with Philips, the large electronics company. And they had a development lab that was doing a lot of stuff for the military. And one of the guys who was with Philips, his name is Folke Hector. He was about 10 years older than me, and a really good engineer. He had both, say, good feel for theoretical stuff, and also he had very good practical knowledge. And he was also very entrepreneurial. We started to work, in inertial guidance, it's very important with Schule tuning. The idea that you're picking up acceleration and if you tilt the accelerometer a little bit, you pick up gravity the same as acceleration. Yeah. To get rid of this, if you put it on a pendulum with the radius of the Earth and you rotate, the accelerometer will always be perpendicular to gravity. And that's 84 minutes.
Right.
So we were doing 84-minute systems. And we came up with a very cute idea that you do a pendulum, and then you try to measure the acceleration of the pendulum, and then you arrange a feedback from the acceleration to the torque, and then you can increase the apparent moment of inertia.
Sure.
That was the idea we came up with. And I remember I first rigged up, and I knew that my knowledge of gyroscopes is that if you rig up a gyroscope and you connect a couple of springs around it, you will actually get this feedback mechanism mechanically. So I bought one of these old aeroplane stabilizers, and then I blew air into it. I could increase the pendulum from having, something like, this sort of natural pendulum. I could increase the period to about 5 minutes with this mechanical stuff.
I see.
And then we thought, well, maybe, and then Volker Hector said, well, then we can do it electronically. And we talked to people, you have to have quite a high feedback gain to this, and people, can't be done. And then we rigged up a gyroscope, and with Volker Hector, we closed the loop and worked 84 minutes. That's when I really believed in feedback.
Okay, so then your research work into your thesis already was.
Oh yeah, I mean I was involved with that project.
Dynamics and control.
Dynamics and control. Yeah. And also I was lucky because we had to go back to Philips in Holland to dig up money. And so Volker and I, we were assigned to go down there and talk to what was then Philips lab, which was one of the superb research labs. And I still remember this. We had to go up to a guy named Casimir. He was, physicist in charge of research, one of the old physicists. So you had to come up to him and tell him about this project and get funding for it. I think at that time I was, I don't know exactly what it was 57 or something like this. So that was also, so that was also, I was nervous like crazy, of course. But that was also a very good experience to have this kind of experience at an early stage.
Sure. You got funded then?
Yeah, we got funded.
And okay, then, what was your next position after you got your PhD?
I tell you this, maybe this is something, I tell you this, but maybe we should censor it. Yeah. No, I'll be honest with you. My intention was, that since we had this close relation with Philips, I thought, it would be really nice to work with Philips and to do these systems. And we had actually done some preliminary flight tests and stuff like this with it. So I was very closely associated with them. And then, they wanted to hire me. I said, I don't want a fixed job. But then they came to this, they really wanted to hire me. We can't have a job, it's only interesting to be like this. And then when I spoke to the senior engineer, he gave me a ridiculous salary. So we're sitting talking like this. I really got very upset because I thought I was worth more. Mm-hmm. So maybe I was too but I thought highly of myself. So that's what I thought. And then he said something really, well, for sort of good average guys, that's what we pay. And then I told him, I never considered myself an average guy. So I think we should stop the discussion here. And then I left. So that was how I got out of so I was planning to work on Philips, but it didn't work out.
It didn't work out.
And also at that time, I had plans to marry and things like this because I met Bia.
You met Bia by now?
Oh yeah. I met her in 57. So but we had plans to get married and things like this. So I went home and I looked up the paper and I found an advertisement. IBM Nordic Laboratory is starting up, and they are interested to hire people in using computers for process control. So I went.
So you went next to the IBM?
Yeah. So I called up IBM and said, that sounds interesting. So it took me up for an interview.
I see.
So that's how I.
So that's how you. And was the first problem there the paper?
No. You see, at that time it was. This was in the. Let me check. started with IBM January 1961. So I think, this, I think I started to talk to them in the end of the 60s, say something like October.
In the 50s?
No,
the end of 1960.
In the end of 1960.
Sure.
And what IBM had done at that time, I mean, they had, if you look back, TRW had put the computers on the refinery,
right, oil
refinery in Texas around 1957. And I think it was Tom Stout and his people, Profitmatics.
Right.
And IBM was seeing a big market in taking computers and putting them onto industrial processes. And also they had decided to expand in Europe. So they had set up what they call the European laboratories. And then the laboratory in Stockholm, that was going to be devoted to process control in general. So the idea was two things. I mean, the mission of the lab were two things. Number one, which was the primary, figure out what a computer should look like that would be useful for process control. That was mission number one. And number two, do some credible case studies. And I think I was employee number 13 or something of the lab. And it was a fantastic lab manager. His name is Kai Kingberg. He has an interesting story. His father was a very close friend of the man who avoided introducing prohibition in Sweden. But instead we got a crazy system that was called a book. So you had to buy liquor, you had to have a book. But then he has to leave Sweden. This guy.
It was so controversial.
Yeah, it was so controversial. So he essentially did his work in Switzerland. And he had been working for the IBM Research Lab in Zurich. And then they put him onto the Stockholm laboratory. And of course that was pure Klondike at the time, because they had the funding, they know the broad directions, but it was big confusion how to go about to do it.
Sure.
So my first assignment was actually to go to, first of all, to study the field in general. And secondly, to go to France on a project where they were proposing to put a computer onto a French nuclear reactor. And this is probably also something I should say. But I had, one of my great shocks in my life, because I had, up to that time, had the impression that industry is extremely well organized. They know what they are doing, etc. Yeah. And then we came down there to Paris. We're sitting there and looking at the requirements and things like this. And because it doesn't take a rocket scientist to figure out the reliability and availability is one of the key issues.
With the nuclear
reactors in particular. Control, yeah. And even if you're not going to do, the safety circuits and things like that. But you really would like to have reliable stuff. So we just did, a very quick, so to say, estimate of this. And you were
failure rate.
Yeah, your failure, and you were far off. And then, you had these sort of IBM managers, in dark suits and extremely executive, and you're very impressed with them at the start. They do all this bird chart and things like this. No problem, we'll fix that. And then we came back and said, that's not going to work. I go to San Jose and fix that. So then the Sumo come back with another solution with several computers, and redundancies. And then you look at this, it's not going to work. So that was one of my big shocks.
Now, was this the 1620 that you had?
No, at that time, 1620 did not exist.
Wasn't out yet.
It wasn't out yet. So no, it was actually special engineering.
Oh,
special engineering. So we called up our boss and okay, come home and we look for something else. And they were looking at two things: steel mills, and also they started to have some preliminary projects in the paper area.
Which, of course, would be an important industry in Sweden.
Exactly. And Finland, and North America, Canada.
Yes, lots of places. So then the control problem that you got into with IBM, was this the process control?
No, we were looking in general, we were doing a lot of, essentially we were doing a lot of studies, looking at process control, what were the needs. Mm-hmm. And of course, one reason I liked to join IBM was that during the work on inertial guidance, I really became interested in computers. I still remember that in 1955 I did my first computations. At that time, there was only one computer. And that was a copy of a Van Neumann machine that was built by a team of scientists who were sent over, to learn about the Van Neumann machine, come home and build one. And the machine did not have an assembler. You programmed in machine language, and you had paper tape. So we were using this for the guidance calculations. And of course, one attraction of this defense problem was that you got access to the machine.
Mm-hmm.
So at a very early stage, we were able, and we did, you essentially run the machine yourself. You came in with your paper tape, you loaded them, and you put on the switches. There was a loudspeaker, so you could hear when it went to a loop. Then you immediately stop, went out, let the other guy come in. And we had money to do this, because we worked on the defense project. And then also in the guidance systems, of course, you had fantastic requirements of computation precision. And we went into things like, pulse feedback and, the sort of differential, what do I call it? DDA, differential
analyzer.
Yes. No. It was sort of an analog computer.
Digital differential analyzer.
Yeah, exactly.
Yeah.
So I really became very interested in computers. So that was one big attraction of IBM,
to have access
to computing and, to learn more about computers.
Yeah. Okay. So then, when did the paper project and system identification stuff?
Okay, that actually came a little bit. I think during the '61 we were talking to paper industry, but nothing very specific were coming out of it. So the IBM manager went out and said, well, he's trying to get case studies, and he had money. So he said, well, I can put people onto this. Mm-hmm. Are you willing to do something? But nothing really materialized on the paper side. And then I was instead sent over to IBM Research in the States.
This is when you came to San Jose.
Oh yeah, that's when I came to San Jose. That's when we met.
Yes.
Sure. So sort of an interim period. I actually first came to the math department in Yorktown Heights. Yes, I was in the math department for a while in Yorktown Heights, and then they asked me if I wanted to move to Jack Bertram in San Jose.
I thought that would be fun. Sure. What were the problems that you worked on there?
Oh, at San Jose, I worked on stochastic control. In the guidance problems we were actually using a lot of stochastic models for gyrometers. Mm-hmm. So it was typically so we were pretty well read up on stochastic processes and things like this. The models were working very well for gyrometers. And this was at the time, when I think your student Gankel.
Yes.
We're doing the separation theorem.
Yes.
So we picked up on the separation theorem, and we started to learn about this. We also looked at, the influence of sampling rates in LQG type of problems.
Sure.
And I also did a short collection of problems for Federal Systems Division, which had to do with the supervised guidance system. If you do LQG theory, and stochastic control, and you knew about inertial guidance, it was very natural to start to look at hybrid guidance systems, when you're bringing radio signals, when you're bringing velocity signals, and things like this. So I worked a bit on that with the Federal Systems Division.
Yeah, that's right. The Kalman filter and all that stuff was out.
It was out. It was
beginning
out.
To.
And also, Kalman came by the IBM Research quite a few times. I mean, he gave lecture series and courses and things like that.
Sure. During all of this time, from the guidance stuff and into your IBM. Now, once again, who were some of the key mentors? That you would identify?
I would certainly say Ulf Grenander. I mean, in Stockholm University. I mean, he was, first of all, he gave fantastic lectures, and I mean, he was a big switch compared to the professors we have had before. I mean, he was, outlining the big pictures, and then he asked you, to do the details yourself, and he was fantastically willing and interested to talk about problems.
I see. Yeah. This was in stochastic processes.
So, at that time I was looking at problems like, stochastic differential equations with noise in parameters. And stuff like that.
Yeah.
And another one was Bengt Joel Andersson, the professor in mechanics, who got all these kind of things started. At IBM, it was certainly my manager, Kai Kinberg, and then Jack Bertram had a tremendous influence. Jack had a very strong personality.
Oh yes, indeed.
And also, when Rudy was coming back, I had a very good interaction with him, so I learned a lot from him.
Okay. Well, let's jump ahead a little bit now, Karl, and tell me a little bit about the history of the self-tuning regulator. I mean, I know that in the paper industry you got involved in system identification.
Yeah.
And when did this minimum variance stuff
okay.
come in?
Well, it went like this, that when I came back from USA and back to the IBM Nordic Laboratory, Kimber came and said, okay, now we got a project running with Billerud company. It's going to be a real project, and he wanted to put me in charge of control. So it was a big project team, and they wanted me to put in charge of the control operation. The first task was to figure out, okay, do we have some good control problems around? So, we spent quite a lot of time at the mill, talking to the people working there, and trying to understand what was going on, trying to understand what would make sense. And we quickly identified a couple of problems that had to do with steady-state regulations of variables that are very important for quality. And one of the key problems is what we call the basis weight, essentially the thickness of the paper. And they were making craft paper, for paper bags and things like this. And also to control the moisture content. And there's a very good economic incentive for it, because if you reduce the fluctuations, you can move much closer to the set points, and then you gain on average. And if you have something that's running 24 hours a day, and you can improve this by say, fraction of a percent, it means money.
Yeah.
With the moisture content, for example, you would like to bring down the moisture of the paper, but it takes energy to bring it down. So you would like to bring it down, just to the barest minimum you have to do to run. And also, it runs much better in subsequent processing if you do this. So we started to look at this problem. And so I said, okay, that's a good problem to look at. And also, switches and other quality control problems. But the one that related to the minimum variance is this business about fluctuations. And if you look to this, this is a very typical stochastic control problem. If you log the variations, that's a stochastic process. You can characterize it by, it's not stationary because it's drifting. So we said, okay, we need to have models. So we started first of all to go down to the middle, and then started to make models out of physics. And we hadn't got any measurement equipment, so we had a couple of months to do something like this. And I still remember that I had a 17th order differential equation that were capturing the paper. That was very proud. So I was developing much work. And then we had the idea, of course, that the only way to figure out what was going to happen would be to perturb the inputs and look to see what was going to happen to the outputs. And when we did the first measurement, we didn't even have to do any calculation. I just threw away my 17 different equations right away. And then, we saw very clearly that what you really had to do, you had to sample. We would really like to have a way to obtain a sampled model that would be capturing both dynamics and noise from the sample data experiments. That was really what we had. Sampling rates were typically 0.5 minute or something like this. And we also had a feeling for that, the only way to do this, since we had so much noise, was to perturb things a little bit up and down like this, and then measure what's coming out in the output. And at that time, I'd also recruited another person to my group, Torsten Bolin. He was a classmate of me. He was in the same class as I was. And we also had similar interests. I persuaded him to join IBM. And then we said, well, we really have to do a little bit of theory for that. So we said we have to essentially develop a theory which will essentially give us the dynamics and the noise model out of experimental data. And at that time, there were also people at IBM. I think there were some guys at Berkeley who was also toying around with the idea. Since I've been here, we had quite a lot of interaction. But we essentially developed the maximum likelihood technique of estimating dynamics model. This AY is equal to BU plus CE.
RMX.
The RMX type of models. And originally we thought that, if you have the RMX, that we had actually other models before. We had one model with the dynamics and then a parallel model with the noise. And then we said, well, then we should do realization and do Kalman filter theory. And then, of course, by looking at this problem, we said, well, look here. If we did determine the RMAX model, we have the Kalman filters are automatic. So we are estimating the Kalman filter gains. Right. And then we said, well, now what sort of control should we define? It was very natural to minimize the fluctuations. And we were very well aware at the time, that you had intrasample variation. But we said, we have to do something that is reasonably buildable. So if we're going to do something, there is no way at all we can do theory where it is start to take care of intrasample variations. So, okay, let's just look at the sample. And originally we were doing LTD type of calculations. English, but then we said like this, well, since we only have polynomials, okay, why should we bother to introduce matrices and things like this? Okay, no. And then we said, okay, there should be a way to do a theory that only deals with polynomials. So that's how the minimum variance theory came around. Yeah. And then, of course, it was a very nice match, because in the pure minimum variance control, you're just minimizing the one step ahead control error. Now, when you do maximum likelihood estimation, that's exactly the criteria that you minimize in the field. Yeah. So we started to write Fortran programs to do the maximum likelihood, and we did the experiments on the plan. We had a lot of discussion to persuade the people who could actually perturb the plan under normal operations. Yeah. And we made a deal with them. Am I talking too much?
Well, I think we better. It's fascinating. But no, I really would like, at least in the few minutes remaining of this part of our interview, Karl, to ask you to tell me a little bit about Lund. What was your philosophy in getting started there? What led you to agree to become professor of control at Lund?
I really enjoyed my situation at IBM. I mean, I thought, it was a fantastic company. I had lots of freedom. You could work on exciting problems. And then I still remember, and also my sort of plans were to go back to the United States again. I mean, that was in the books, and we had nice things sorted out. Because, I mean, I learned so much here. And then there was a professorship, announcement of a professorship in Sweden, a full professorship. And I said, okay, why don't I just apply for it, see what happens. And there were quite a few people applying, and then what is happening? It's a strange thing to become a professor. But to cut a long story short, I was appointed. Mm-hmm. And at that time, the appointment paper was signed by the king.
An offer you couldn't refuse?
No, and then I said to my wife, okay, let's go down there and talk to them before we make the final decision. And also, I mean, let's see this as sort of a 5-year project. At that time, I also had a little daughter. So we went down to Lund. We came there in May. They were just starting up a new engineering school. So Lund is an old university, and then they started up an institute of technology parallel to this place. And also, I've always been interested in education, because I knew there was so much stuff you really should teach people instead of just the servo mechanisms that were being taught in Sweden at the time. So this was 1965. So I said, okay, in here you can really have a mission. And Lund was a very nice town, and in May it was absolutely splendid. So I looked at it, so we said, okay, well, let's stay. Let's skip the United States for a while. And then I came there, and I wanted first to get a leave of absence for a year to finish off at IBM. But then the dean said, okay, why don't you come down to lecture? So we decided, okay, I go down to lecture, and then I go up to IBM once a week to sort out the rest of the thing we were doing there, because I didn't want to give it up. And then I also had, professorship at that time was great, because I mean, I had my positions. I could actually have 5 technicians working full time. I could have TAs in other words, graduate students, and I could hire a lecturer. I could hire a postdoc. And then I had a fat chunk of money to buy equipment. So that was challenging. And also I had a list of equipment that they wanted me to buy, that they had made up before. But fortunately, I got hold of that list before they bought it. So I said, okay, stop that.
Now, was it your decision to start a department of control?
No.
Or was that the original idea of the organization?
Okay, the idea of the organization was that this was a very European thing. So, you have a professor for each subject, and then you have an area. And one thing that when I came there, I said, in Stockholm, for example, all control courses were given by one professor for mechanical engineering, electrical engineering, chemical engineering. And that was something I liked very much. It was exactly the same setup. In Stockholm, it had started already to separate a little bit, because if you do this, you have to do a very good job of teaching, because otherwise chemical engineers don't like it. So we said from the very beginning that we really have to do a good job of teaching to make sure that we can maintain this unit of control. And also originally there was not very much time. We had essentially 2 courses allocated, one introductory course and one advanced course. There's always fighting for coursework. But I came there and I essentially designed a control course from the first that combined frequency domain and state space relationships. I knew, okay, that's the only way to do this. So we did frequency domain and state space for the introductory course. And then we had for the advanced course, we did stochastic, nonlinear, and sample data.
Now, was this your first textbook associated with that course, the regular theory?
Yeah, exactly, yeah.
But,
so there was not much around, so I wrote a textbook in Swedish very quickly.
Yeah. All right. I have some other things, but I think maybe we all...
The interview with Karl Aström, and now we have a panel of interviewers, and I'll introduce everyone first, and then we'll start off with just open questions. The panel is Jean Franklin from Stanford University. We have Bruce Krogh from Carnegie Mellon University. There's Herb Rauch from Lockheed Martin. On this side, we have Shahram Sharuz from the University of California at Berkeley, and Steve Yurkovich from the Ohio State University. And my name is Linda Bushnell, and I work at the Army Research Office and Duke University. So we'll start off with whoever wants to make ask the first question.
Bruce, why don't you start off
Okay,
with that question we had a follow-up?
Oh, okay, yeah. Why don't we pick up with that question about how did you get to do perturbations on the planet?
First of all, we did a lot of calculations on natural perturbations, and if you really looked at this, we saw nothing sensible was coming out of this. There was a lot of ambiguity. You couldn't really see what was happening. Then we had to deal with the quality control department and say, well, if we do the experiments, why don't you do extra careful monitoring of the control quality? And then you send up a signal immediately if you see something happening with us. Or why don't you let us do a try, and you try to figure out if we are spoiling your quality? Well, they agreed to that. And then it turned out that we did an experiment. And they were analyzing the quality. Well, how's the production run? Oh, it's running fine. They said, we have actually done an experiment. And the reason we could do this, we established very good relations with the people who, the operators who were running the mill. And so we talked to them a lot. We brought them up to the computer room. We printed out, postcards and punch cards with them, and we explained to them what we were doing. So we had a very good rapport with them. And then we asked them, if we change this weight a little bit, do you think for a couple of minutes, do you think very much will happen? Oh no, not much will happen. So we had very good reassurance from them, that we can do the experiment. And of course, once that had happened, it was not a big deal to do it. But even today, I think that's one of the key problems we have in control, that people out there are extremely unwilling to let us do experiments. And my argument is like this. If you have poorly tuned controllers, you have larger fluctuations than you would have. So you are actually introducing perturbation to your plant yourself. If you allow me to do a little bit of perturbations on it right now, I will actually get you smaller perturbation in the future. And I think this is an argument that often goes home.
Yeah, I have a question about the time you were a student and then when you started as professor at Lund.
Yeah.
When you were a graduate student, what were the important textbooks? Right now you go downstairs and see lots of textbooks for graduate students.
Yeah.
For you, what were the important textbooks?
Okay, I think the important textbooks were for example, if you take control, I studied Newton Gold Kaiser very carefully. Another book I studied was CN, Engineering Cybernetics. We studied quite a lot of things on stochastic processes. We studied calculus of variation. See, at that time, there were really no, Pontryagin's books came after I finished my Ph.D., for example. So there were not very many books around. We studied a lot of mathematics, a lot of probability and things like this.
And when you started at Lund, you started taking grad students and PhD students.
Yeah.
How many PhDs have you supervised? And do you know where they are?
I think I've supervised 44.
Right.
And about, roughly speaking, I think about 8 or 9 of them are now full professors. More than half of them are working in industry. One is working in the finance department in Sweden. So they are spread out quite a bit.
A question for you on education. Things that Jean mentioned to you brought this to mind. Some of in my mind, there's two issues that are affecting programs in the States in terms of education in general, engineering education. That is the way we have departmental boundaries, which are becoming barriers, or have been for years. And then the other is the 4-year versus 5-year degree. And some of your comments sort of touched on both of those. Can you tell me what your feelings are and pros and cons? Because you're obviously familiar with that state.
I'm personally very much against department bound, in particular for a field like control. My view is something like this. The classical departments, they are relics of the last century, where you had, mechanical engineering, electrical engineering, chemical engineering. And if you look to the problems that are facing engineers today, they are very, very different. I mean, you have one category that you can call systems problem, which we are close to in high school, and the telecom people. You have a lot of material problems, which is cutting through another way. And I think, if we can somehow loosen up the department boundaries, that would be tremendously important. And I've seen some universities in here which have been quite successful in doing that. I would say, I think Caltech is doing a very good job of it, for example. There are very low department boundaries there. I think in Michigan, there are quite large departments, but there is quite a lot. At least I was there a couple of months ago, and I got the feeling that they have a pretty good way of handling this with respect to that. With respect to the 4 or 5 year programs,
in the so-called professional degree idea.
I'm not fantastically. I don't really have a strong position on the professional degree. On the other hand, if you look to the 4 or 5, one criticism we are getting in Sweden, for example, is that we have takes too long for us to get a PhD. The average time, the nominal time to get a PhD when you pay for in Sweden is 6 years after the master's. We get a lot of flack for that. And also, if you look to I see our own engineering program, which I think is easier for me to criticize. We are now 4.5 years, and I'm not sure that you are a better engineer if you study 4.5 years than if you study 4 years. The courses you have to, there are so many things you can study, but you cannot possibly study anything you need anyway at university. And I've asked students, for example, who are in the last year, for example, do you feel that you get very much smarter by taking this advanced course or this advanced course? And many of them, it's just another course. So my feeling is that I'm not sure that you become a better engineer by studying for 5 years than by studying.
Actually, this is kind of related to the education system, but I'd like to know if you could explain different work conditions and opportunities to achieve that you see between, say, Sweden and the United States.
I think, that in retrospect, that I've been very lucky because there are tremendous advantages if you look at the Swedish system. Because the way it's been working, it's that, for example, if you're a professor in a Swedish university, you can do quite a lot of things, anything you like to. And also, the way the system used to be is that you can have, say, 3 or 4 PhD students without having any research contracts. Because with a position of a professor, it comes certain amount of resources. Now that means that you can actually endeavor on doing things without getting into, a lot of contract assets. Now this situation is changing in Sweden. I mean, now we have professors, for example, who are appointed without having a bag of money or a bag of resources. So, I mean, we are moving towards the American system. And of course, there are also professors in our place who have been abusing the system. But I think one advantage that I've had is that to have this sort of, say, freedom to do, say, fairly long range things without, thinking about, is this contract going to run out, or are we doing something that's sensible or not? Of course, you have to be responsible. I mean, if you're in an engineering school, right, we should really educate engineers. We should do research that is. I've often had many problems I've been interested in, but I said, okay, it's not really mainstream, so let's put them until I retire.
Karl, let me ask you about the education again. How have you organized at Lund, and what is your ideal picture of the mix between theory, laboratory, and industrial experience for let's say the master's candidate. The student who's going to go out and be a professional engineer rather than the PhD at this point.
First of all, I think in general, and we have also made this mistake, I think, a lot of the master's program is geared towards preparing people for the PhD. Mm-hmm. And I think, if you take control, I think one would take a different outlook. You say, it's a person who only takes one course in control, and then he's going to go out in industry. You take a very different attitude and say, well, this is the first of a sequence of 10 control courses.
Right.
And I think that's something we have to address. What we have done in Lund is that we have integrated. We have a system with lectures that you give to a large class. You break them up into problem-solving sessions where you have about 20 or 30. And then we have introduced labs that are integrated with the course. So if you take an introductory course in control, you get lectures, you get problem-solving sessions, and you get labs.
How many total weeks would we be talking about?
We are talking about 14 weeks.
Okay, now, the typical U.S.
Yeah.
semester.
So it's a typical semester course. And typically you would have, the way we have done, the labs are the hardest ones because we have classes of about 300 students. So how do you do labs with 300 students? Well, we typically do, you do lectures for everybody for about a week, and then you have the first lab, and that goes typically in a 2-week period. The students can sign up a slot from 8 to 12, from 1 to 5, and from 6 to 10. And we have something like at most 8 parallel setups, so you can bring in 16 students at a time. And then you can do 48 students in a day, and then in 2 weeks you can do enough. And there's enough flexibility so students can fit it into their schedule.
And as I understand it, there's no lecture during that 2-week.
Oh yeah, there are lectures going on.
Oh, the lectures going on as
so
well.
Yeah, so the students,
So you have to schedule those
so the
carefully.
students, well, we just send up sheets, and the students sign up for the slot that they like. And what we intend to do when we get, say, in our future plans, is also to have some labs that are always sitting there all the time. And of course, with this lab, it's only 4 hours. I mean, it's typically set and organized, but at least they get a little feel for reality. We do it with desktop processes, and then a PC is sitting next to it. You know, they get a feel for, well, there are saturation and actuation. There is noise coming in. The models don't quite work. We typically do 4 of these labs in the introductory course of control. And I think that's a sensible way to do it. In the advanced courses, we have always made, there we do projects instead. So in all the other courses, there's typically a 1-week project that students have to do. So they take the lectures, and then they have to do a small project in 1 week and document this, and some of them are selected to present it. And I think that's, and I think it's useful to mix things like this.
So you're looking at me, so I'm going to ask the obvious question, which I can't imagine why other people haven't asked. Say a few words about the different aspects of the relation between the university and industry in Sweden, and then kind of if it's similar to in the United States or different. I'll give you some hints.
Okay, I'm not quite sure what you mean.
Does the industry kind of influence a little the courses you teach? Are there, is there some feedback, when people go to work for industry, do they say, gee, we should have done this, that kind of thing?
Okay. There is a formal structure because we have, for all education programs, there are educational committees. And in these committees, there are always industrial representatives involved. Also, we have an overall committee that oversees the teaching for example, for electrical engineering, computer engineering, and engineering physics. There's a committee for that. On that one, there are industrial representatives. And also, what we are doing ourselves, I think we have had a lot of master students, something like 500-600 of them. And we keep, say, fairly good informal contacts with master students that go out. And we often get very useful feedback from them. Said, oh, you should really drop that. It's kind of ridiculous to talk about this. Others are saying, well, this is something that's emerging in here that you really should take care of the university. And I think there is an advantage in, there are many big disadvantages in a small country with only 8 million people. But there is one big advantage, and there is a lot of informal networks. So, for example, you very often find either it's one of your school friends who are sitting somewhere in a good position, or it's a friend of a friend. So I think in a small country like this, which has a fairly stable population, there are many informal networks. And when people exploit this, it's very advantageous. Of course, it's not always used.
And then, do you think that this kind of thing is happening in the United States, or you talked about different universities where you felt something.
Of course, I don't have a complete picture, but I think there are some places where this is working quite well in the United States too. You have these visiting committees, for example, where you often. So I think in the good schools here, it's functioning very well. I think for example, we in Sweden and Europe could actually benefit to have visiting committees of the type that you have in American universities.
question. Do you believe that there is fair balance between mathematical and practical development in our area? And if no, what should be done?
I'm not sure. And I think that it works like this. I was at a session today from there was a guy from Integrated Systems who gave his view of control. And I think if you look to control, it touches upon very, very many aspects. I mean, it touches upon model building, it touches upon implementation, it touches upon computer science and things like this. And I think that if we have students who are a very heavy emphasis on the theoretical side, and they are not in touch with some of the other things, they will have a very long start at theory. And also I think that I don't think control engineering will get the credit it deserves unless we have quite a few people in our community who take what I call systems responsibility.
Let me pick up on this theme a little bit, just because I wanted to ask you. You mentioned I think you said they were putting together a group on theoretical inertial guidance, or you described one of the groups as the theory side. And I was curious whether you, since this whole issue of theory versus practice has been discussed on and on, have you seen? I'm curious what that meant then. And also, if you've seen a change, does it mean something different now?
I think the name was totally irrelevant to this discussion. I think that was a way to put defense money onto the university. So it was totally an administrative. And because we have never had the situation you have in here, that the Army and the Navy are supporting university to a very large degree. I mean, it happened during the war in the aero industry in Sweden, and it happened with this theoretical inertial guidance groups. That was a way to say, oh, this is work, defense work done at the university. That's really what theoretical meant.
Yeah. But even later, when you're talking about the minimum variance control, you said, well, you came to a point where you said, well, we need a theory to do this. We're going to take a couple months to develop this. So you did turn your attention when you were
sure. I've always had a strong theoretical view, to say so. I mean, I think it's partly what you're interested in. And I think the advantage by doing that is that you are not solving a specific problem, and you are lifting your eyes up a little bit on a higher level. And by doing this, first of all, what you can do is much more general, and also you can see things that you would not necessarily see otherwise. For example, if you say that you're jumping from doing inertial guidance systems to controlling paper mills, okay, what is the connection? But clearly the connection is that in both cases, random phenomena have a very significant influence. So I think there's a fantastic value in, and I think that's the reason for the success of control.
Do you think there's been a change in industrial attitude about that kind of perspective? I think we probably all agree at this table that's a great way to pursue problems. But do you think there's been a change in the attitude in industry about letting people pursue problems in that way at all? Have you seen any changes?
The reason I'm hesitating is that I don't think there's a simple yes or no. I think it very much depends on who are the managers in the industry. I mean, who are the guys who are running the industry from? And I've seen some, for example, the guy we had at IBM, he was tremendously important supporting this. I mean, he said, he was, from that perspective, true vision. I mean, he said, okay, remember this, that, what's important here is what's important in the long run. I mean, don't take shortcuts. I mean, if you think, it's necessary to do something like this, go ahead and do it. In the end, he said, but remember, in the end, it has to be useful. So what I think, is what we really need in industry is, managers who have guts enough to keep umbrellas over the people who work for them. So, they make sure that things are going in the long direction, but they don't make, the guys, the young guys who are working for research, they don't pressure them too much, because then, they can't be creative. And there are good managers like this and there are bad managers like this. As soon as they get nervous, you must finish this on Monday, things like this.
Carl, I had a colleague of mine recently sent an email, and he said he was a theoretically based guy, didn't get out to industry much, and he said, someone told me that 95% of the control that's done out in industry is PID.
Yep.
He said, is that true? And I referred him to your book,
Yep.
Your ISA book, because I remember a quote in there, you said, a new era of PID is evolving. I hope I'm not misquoting something. I'd like to hear your views on this. What's the future for the techniques that we're developing and the funding and this sort of thing as you see it?
Okay. PID was something that I learned about, I would say, really learned about too late in my career. And I think, what is happening right now is that there is a lot of control problems that are solved by PID control. And one reason for this is that, first of all, there are many simple problems out there in the industry. There are lots of, say, fairly simple control problems that you have to deal with. And also, there are so many people out there who are, so to say, brought up with this technology. On the other hand, I also think that there are quite a few problems where you can actually, do much better. But I tell you my own experience of that. There was a time in the end of the 70s where I was getting kind of like you do. For various reasons. And I said I needed to have a break. And at that time, it turned out that they had a very nice scheme where professors at university could go out and work for small companies. The scheme was something like this. You maintain your position at the university, and small companies could send up to a body proposals of various types, and then they tried to match them up with faculty, and then you could take over for half a year or a year to work with the company. And then there was some subsidizing, so the company didn't pay them. So I was thought that would be a nice change to get a break. So I worked for a very, very small company. It was something like 40 people. There were 3 engineers down the road from Lund. It was called Telemetric. And they were doing 2 things. They were selling stuff that was manufactured by an English company in Sweden, putting things together to make systems. And they also did their own microprocessor-based systems. And that was called in, sort of research project to do this. And that's when in the coffee discussions and the stuff like this, and many other things, I really started to learn about number one PID, the other one selector control, which I think we pay very little attention to. Also, I had the advantage to be able to talk to the people who were actually designing those controllers. And many of them were analog-based, and they had fantastic ideas. They were not spelled out, in the way we would like them to have spelled out. And they were not, put onto the microprocessors and stuff like this. So that to me was a big revelation how much you can do with a PID. I also think there's another factor that we're totally missing in control. And that is, we take always the plant for granted. The plant is given. And what we really should say when we get a problem, we actually have possibilities to modify the plant. To move sensors around. One thing we did with the paper mill, we were actually making much smaller mixing chests, where you have mixing around. Smaller mixing chests with much more energy, for example. You can move sensor, you can put in other actuators. And what you would like to do is that you would like to modify the process in such a way that it becomes simple to control. So I must say, I totally misread the importance of PID control. That's why I wrote this book. So it's a late amendment.
Yeah, I have a question. If you could, if there were any women in your program when you started out, or your graduate students, and what you see.
Okay. Yeah. I've been doing extremely badly on that front because of these 48 PhD, none of them is women. But again, I've been another late amendment. And I think the reason for it is that first of all, there are very few women in the engineering schools in general. And also, the first course in automatic control, it used to be in the 4th year, now it's actually down in the 3rd year. And when they come to the 3rd year, many of them have already decided, they are already going to physics and stuff like this. So right now I have two women who are doing PhD studies with me. And we have been doing recruitments right now. We will probably recruit another one right now. And I'll tell you about my scheme. What I do is that I don't like quotas, I think that's a really silly thing. But what I do is the following. On the introductory examination, the first course in control, I look at the grades. And all girls that are, all women who have full grades on that, I write them a letter. I say, well, congratulations, a very nice result. Here's a book on control that you might read, and control may not be your thing, but why don't you come up to me? And of the few women that are around, I've recruited 2 super ones with that scheme. There have been other ones who have come up and talked. We found they are not at all interested in control, but with the contact net I've had, I've been able to channel them to a lot of other interesting places. So it is changing, but it's changing too slowly.
Karl, I'd like to go on another branch of your contribution. You mentioned that you went to IBM partly because of computers. Some years later, something called Simnon showed up on the table. Tell us about that. Why did you decide to go into computer-aided design?
Okay, well, that's a great question. You know, when I started in Lund, I think I learned a fantastic amount from IBM. You know, one thing you learn from IBM is, to do planning. Another one is to do administration recently. And when I came to Lund, so to say, we said, okay, let's do a plan for how to do research. So we've always been doing research plans, and we've not always been following. But one thing we said, okay, we're going to do 2 things. To be good, you have to focus. So we're going to look at some methodological things. And typically when I came there, it was very natural to start to clean up the system identification. So we're going to look at some methodological, theoretical things, where the goal is to come up with new ideas, to come up with new concepts. And if you can try them out, fine, but that's the main thing. Now, we also have this side that we have to serve industry. And we have to, most of our students are going out to industry. So if we just do that, we will have a very weak coupling between research and the education, which I think has been very bad. So I said, also, we will always have an applied project. So we said, and then what I mean by an applied project is a project we do with outside partners. And it's typically a project where we are only doing a very small part. And the reason for that is, number one, to broaden your field for what applications of control are. And secondly, to find theoretical problems which we have not yet tackled.
Excuse me, is this for the entire group or for each individual?
No, that's for the entire group. Okay. Yeah, for the entire group.
Sure.
No, for the entire group.
Okay.
Also, another thing, I'm glad you mentioned that. Also, you create tensions. You create tensions between the guys with their head in the skies and the guys with their feet on the ground. And this tension, I think, is tremendously important to have a healthy research.
Very healthy.
Now, one thing we discovered very early was that when we were doing the applied work, we needed to work fast. So they cannot wait, say, oh, I can't do this because I have a lecture on Monday, I have a lecture on Friday, and things like this. So we said, well, we really need to develop tools. And at that time, I also made another decision. We wanted to have our own computer, and around I think it was 69, we bought our first computer, our own computer with our own little book. And then we said, okay, we are going to develop tools so that we easily can do design, system identification, all that kind of stuff. And what happened was that I had a very talented Ph.D. student who we also did the mistake of putting him in charge of the computer infrastructure. So, I mean, he took quite a long time to finish his Ph.D. because of that.
What was the computer?
It was a PDP 50.
15,
yeah?
Okay.
So, it's sort of a strange animal. It had 18-bit word length, but it was a fine machine. I mean, it was the sort of late generation PDP-9. We had this by ourselves, and we were typically allocating hours. You run it yourself for 1 or 2 hour slots, and you signed up a machine to run it. That's how we did. And this guy, Johan, he was very good. He had a very fine feel for this sort of stuff with the computers. And at the time, we have seen the Rosenbrook's work on CAD, which was essentially a question and answer. And we were sitting there and discussing, that's not the right way to do it. We should really start to do command line interaction and things like this. And then we started to do a couple of packages. The first one we did was actually something called INPACK, the identification package. And then we did another one we called SynPack, the design package. And then we said, well, what we should do, we will do one common graphical user interface for all packages. We did something that was called InTrack. So the user always sees the same thing, and then you do the. And that we did at a very early stage. And then I had a master student who came to me and said, well, you know, I'm an electrical engineer. I like to control stuff, but I'm really interested in computer science. Can you find a project for me? So we said, well, we would really like to have a way to simulate non-linear systems. So we put him onto the task, and we showed him the stuff we had. And then he actually came up with Simnon as his master student. So he had a sort of very primitive version of Simnon running as master student. So that was an interactive simulator, I think it was 72 or something like this.
Yeah.
And
all these were running on the PDB-15.
They were running on the PDB-15, written in Fortran.
Yeah.
And so at that time we had quite a nice package to do this. And then we said, this looks so promising, so I went to get funding to do another development of that, to really turn it out to something we could use instead of the typical student software. So we hired him for a year to do what would really become proper Simnon. After that, he said, I'd like to do a PhD.
Was this
Elmqvist, Hilding Elmqvist. You know, he was at Stanford, you know, like many of our students came there later on. And so we did Simnon. I said, well, how about doing a PhD? I'd like to do this, but I'd like to do something that's more advanced. And then he did an object-oriented modeling language. He said, you know, we have to get rid of this stuff with causality and things like this. We have to do this in the right. So he did an object-oriented modeling language that was Dimula. And the only language he could implement it was a Simula. You know, which is but he did this for his PhD dissertation. And that software is not actually being marketed way long after, because now it's the right time to do it.
Yeah.
So that was essentially the push from the fact that we had application project, and then essentially the input of a very smart student. That was Simnon, the story of Simnon.
What's the outcome of that now? MATLAB seems to be taking over the educational world. Has it taken over Lund as well?
Oh yeah, you know, what we did is that we were running this project up to the end of the 80s. So around the 80s, so what we had then, and actually I think we saw MATLAB at a very early stage, because we had a conference on numerical methods in control around 1975 or something like this. Yeah. Clean Morley was invited, and Clean Morley demonstrated MATLAB at the time. And we had this software. There was a big discussion in the group, you know, to do the sort of next generation of this. And we decided that we were not going to do the next generation. We were going to replace Synpack with MATLAB. So what we did is that we said we're not going to continue this. So we essentially closed down the activity we were doing in the end of the 80s, and then we went for MATLAB. And we stuck to Simnon, you know, for quite a long while. But I mean, right now we are using we're still using Simnon a fair amount, but we are using, say, the MATLAB,
the Simulink,
and the Simulink environment. But also we did another interesting thing. In 1985, we said that it was a very good time to start to look at computer-aided control systems in engineering. Because now, you know, in the end of the day, we saw the workstations and things like this coming. We also saw the drawback of doing Fortran programming. But in 1985, we started a new project, computer-aided control systems. And we said, we now have workstations, you have totally different software environment. And we started broadly for 2 years to explore different things. For example, we did knowledge-based user interface and system identification. We view control system design as being sort of a language problem. You know, you have design methods and you have attributes and things like this. We looked at modeling, and we looked at doing things that were extremely user-friendly. And then after 2 years, the contract was we should focus on one area. And we decided to focus on modeling tools, because that was another thing we have seen in the project, that you spend a lot of time on physical modeling. There's really no computer support for that. And that is now bearing fruit. So we have had 2 PhD dissertations finishing on modeling tools. And there's a piece of software called OML, Object-Oriented Modeling Language, and a simulator called OMSIM, that, which is actually now available. You can pick it up by anything. But the idea is you cut the system into subsystems, and then you describe what's happening at the interfaces. And then for the subsystem, you just write balance equations. and then you let the software clean out the rest. So it's something we are quite excited about. But I think that's another useful thing I learned from IBM. You should stop projects and you should stop projects.
Yeah.
If it hadn't been for IBM, we would never have ended our computer-aided at the right time.
Yeah.
So that was something I'm grateful to IBM.
That's great.
You know, when you were describing your own career, and then you talked about your group being involved in projects, it sounded like you were so often involved. Control's always got to be part of something larger, and you were also involved in just current emerging technologies. What are some of the emerging technologies you see today that control engineers that want to have as exciting a career as you've had, you'd suggest they get involved in?
Okay, I think there are very many things. First of all, I think we had a session here on application of adaptive control. For example, I think automotive stuff is tremendously exciting. And of course, to do this, I think we must also get control engineers who really get involved in implementing things like this. But I think automotive is tremendously exciting. Because we're going to get much more electronic coming in. I think it's really going to change things. I think if you look at scientific instruments, I mean, you look at this, active optics and stuff like this. You have the mirrors, and I mean, you can bend them around. So I think there are very special instruments where control can really have, very, very major impact. Something that's a little more speculative. I think that personally, I'm quite interested in learning systems. I think the sort of degree of learning we have in adaptive systems, even in neural network and things like this, are at quite a primitive level. I have grandchildren right now, so I mean, if you see, how grandchildren are doing things, if we could just, get, a tiny little fraction systems with that kind of ability, I think that would be, fantastically exciting.
You see applications where learning systems will have a home or a place to nurture? You see some places where it seems like they're really supporting.
I think it's too early to start. I think this is, in a certain sense, fundamental. But if you can have systems like, take an example. Imagine that you're going to learn a child on a bike. You put the child on a bike, you run after him like this, and then suddenly they start out to bike. I mean, suppose we could have, control systems.
In my case, my daughter didn't learn until I left her alone, and I came home one day and she was right.
Okay.
My help with that.
Okay. No, I think it's a difference when you're a grandparent. And so I think, and I think there are many areas where, for example, there are new materials coming out. I mean, all these, memory materials, I mean, all these sort of strange materials. And I think we're going to see totally new designs of processes. I mean, if you say, integrated process and control design, where, for example, by having control, access to control, you would actually do a process in a totally different way than you would do today. There are some other things. If you look at in the process control area, say if you take pulp and paper, which are still making a little bit of contact with, because of the environmental regulations, they are doing system closures. Which means that, you take whatever is coming out in the output, like heat, and then you recycle this to the input. And you take, rejects like that's coming out, and you recycle this to the beginning. That creates fantastically complicated dynamics. So to be able to deal with systems like this. Take another area, which I was very glad to see a session on here, seeing the telecommunications area. I've been involved in a couple of these sort of research advisory board for companies. I have quite a bit of insight into the telecommunications area. And you look at the way, telecommunications is totally being revolutionized right now. And in there, I think there are zillions of control problems which are not perceived as control problems. Just to give a couple of examples, you take suppose you're going to make a telephone call. Well, you can have a cellular phone, so you can use radio. You can use infrared, you can connect it to you can switch it into a fiber optic stuff and things like this. So how do you manage all this sort of stuff? I think that's a fantastic control problem. But they are still not perceived as control problem. There's a little bit of, these ATM switches and stuff like this, but I think there's some overriding control problems sitting there in the telecom industry that I think are very exciting. Another area, if you take, for example, pharmaceuticals. You know, manufacturing pharmaceuticals are not at all very expensive because they haven't, the products are so expensive, but they are now starting to become very interesting in manufacturing. To take, for example, another thing, single wafer manufacturing in the semiconductor industry.
No, I'll bow to you if you want to ask.
I've got mine. I made a long list, so I cheated.
Yeah.
I did have a couple of other things, and let me just say them for us. We don't have a whole lot of time, but let me just say that the two questions. Perhaps you can interlace these a little bit. One was that I've observed that you do an unusual amount of international collaboration. Yeah. You've worked with people at ETH, at Berkeley, at all sorts of places. Sort of why did you choose to do that, and what impact do you see that as having? Is that something you advise colleagues and others to do? What does that?
You know, I think it's tremendously important, and in particular, if you're coming, from a small country of the size like Sweden. I mean, it's no question that the action is on the international scene, and I mean, if you don't participate in this, you can never, learn. And you can never, pick up things. And I think that really dawned upon me. Number one, when I first saw interaction with the people from the instrumentation laboratory at MIT. I mean, when I saw this guy coming over, that really opened my eyes. I said, oh boy,
these things are going on in other places.
These things are, these guys really know something. And then, of course, when I was at IBM, it was very clear. So that was one thing when I came to Lund. I said, it's absolutely essential, to keep contact and also to keep sending students out.
Yeah. And I know you've done more than almost anyone.
And and also in the United States, it's so nice when a city, because all people are coming through and giving seminars and things like this to you. But they don't go through Lund and give seminars automatically. so we have to go out.
Yeah. And the other question that was interesting, but the other question which you've not really touched on was your involvement in professional activity. I know for a long time you were editor for Automatica, associate editor, whatever the title, George.
I'm still editor. Yeah.
But in terms of national academies and IEEE and those things, what role have they played in your career?
I think both IFAC and IEEE have been tremendously important, because if you take this editorship, I think that's a fantastic way to learn. If you have a very busy schedule, you have a tendency, you have this stack of interesting stuff that you have to read, that I think all of us have. And unless you get enough priority on that, you will never read it. But if you get involved in editorial things, you have deadlines. So
you have no choice.
You have no choice. And I think that's tremendously important. In the same way, these meetings, for example, the CDC meetings. I mean, they are tremendous. That's a fantastic way both to meet people and interact, and also to learn about other things. So, and I think IEEE is much more important for small countries like Sweden, and maybe it's easier for big countries like the United States.
I don't think it's that much different. Not in my experience.
But I think they're tremendously important.
How are we doing, Linda?
We run out.
We've run out. Okay.
No.
It's still going? Oh, right. We're just energized that through. Let me then just ask my last question, which is not particularly more important than any others. But anyway, the textbook business. We've mentioned a little bit your early regular theory, the Swedish introductory control. Steve mentioned your ISA Ph.D. control. I happen to know, I have copies of a book that says stochastic control, and one that says computer control, and one that says adaptive control. Is that the product? Why do you write textbooks? Or books?
Well, I think I forgot to mention one person that was very important to me. That was Richard Bell. I met him at a very early stage, because he was visiting Sweden and to give lectures on mathematics. My math professor was responsible for him, so I had to take care of Dick Bellman when he was in Sweden. And that's something I should have mentioned long time. But Dick said to me, he gave me a lot of advice. He said to me, Karl, you should write books. And so I said, why? Well, he said, people never read your papers. And also, if you write papers, you have these sort of page limits. So he said, you can never really explain, and unless you put in 5 theorems, you would not get them published. So he said, if you would like people to read your ideas, you should write books. Because in a book you can expand on the things that you're doing, and you can, elaborate upon them. So my first idea to start to do books, that came from Nick Ben, and he was the one who persuaded me to do the stochastic control. So I think that was how it got started. And I also think that, again with textbooks, I think it's a pain in the neck, particularly when they come and ask you to do, the 3rd edition and the solution manual and all that sort of thing. But I think it's a very good way to learn. And also, I have another feeling with control, and that is, I think we really have to, compactify the control knowledge. What I mean by that, there's so much stuff around. And then, you start to think about this. What kind of equipment should we give to the next generation? And the only way to do this is in one way or another to try to make the knowledge, figure out, weed out what you don't have to do and put in what you really have to do. And of course, one way to exercise into that, the way of doing that is to work on textbooks.
A young student comes to you today and says they want to major in control. Do you encourage them or discourage them?
Oh, I encourage them.
Do you think it's a growth field?
No, I think it's. I think there are many opportunities in control, but I think that you have to keep an open mind about. You have to think about what kind of things you would like to do or what kind of contributions you would like to do. It's not as easy as it was. I think we were lucky, both of us. And we came in at a stage where, you couldn't fail. There were so many exciting problems.
Everything you looked at was new.
Exactly. But now it's different. So I think, you have to be... We are more like a normal field now than we were at that time.
Well, thank you very much.
Thank you. Thank you.
Thank you. Yeah.
Well, what you're supposed to say at the end, is there anything else you would like to say?
Oh, I'm sorry. The camera's still on. Is there anything else you'd like to say, Karl?
No, I think I've spoken.
So the last question is, if you had the chance to do it again,
would I do control?
different in your field?
I would do several things. First of all, one thing I would do is that I would have learned many more languages when I was young. I
take English, German, French, Swedish, and Norwegian.
Yeah, well, Swedish and Norwegian are the same. But I'm not really fluent in German and French. So that's one thing I would do. I would do if I do different. Also, I think another thing I would do differently is that if you take, for example, we mentioned here the PID control. I think that something I would like to have done differently is to start with PID controls and automatic tuning much earlier. Because that would have, I think, this idea to see where do we find the problems which many people are interested in. So I think it would have been good to turn the adaptive stuff around. First do the PID and the auto-tuning, and later to do it. And that's in a very recent example.
Are there any things that did not pan out the way you thought they would? Is there something you were really excited about the controller and you thought was going to really be a boom, and you're surprised that it hasn't been as important as you thought it might?
Oh, I've had lots of.
One representative.
I think I'll answer it in a different way. You often have these sort of fantastic ideas. You say, okay, I think I got this figured out. And you're sitting there at night, you're doing the calculations and things like this, and you have these beautiful results. They are absolutely fantastic. And then, you check them next day, you do a couple of simulations, you find out, no, didn't work. And so, I've had lots of experience like this. And also, on the other one, things. So I think one thing I've been lucky is that I've been using a lot of feedback. So I'm not being, putting a fantastic effort for something on a very long time, and nothing coming out of it. But on the other hand, I've had a fantastic number, of false starts, and I've been wasting, months and half years on all sorts of crazy ideas which haven't really worked out. But nothing that I've been spending something like 3 years or something like that.
But I was thinking also more on the field in general. perspectives on the thing, because I've heard a couple of people, for instance, R1 Nobel laureate, Herb Simon at Carnegie Mellon.
Yeah.
I heard him speak once. He started to talk about how artificial intelligence was going to revolutionize decision making and everything. And after he finished this, he said, "That's the beginning of a talk that I gave 25 years ago." So
I think I'm a little bit too much of an engineer, to
have this kind of optimism.
Okay, well, we should wrap up.
Okay.
Thank you very much.
Well, thank you. It's been fun.
Thank you.